Okay, we're going to be using those notes for probably most of the week, or at least today and Wednesday. So, and I have your exams. I'll hand them out at the end of class. I'll post the answer key tomorrow. So if you have any questions, and then I'll release the scores sometime later today, which will update where you're at. And that'll be your midterm grade. Midterm grades are due on Wednesday. And I'll probably be submitting a midterm grade just for everybody. So, okay. And then for Wednesday, there's a homework or a take-home quiz problem up here on aromaticity, since we were going to have all the aromatic stuff due, or on the next test, which isn't that far away. Okay, what I want to do is go over some of the aromatic side chain reactions, and then go into reacting the actual aromatic ring. And this is, I think, all in Chapter 20. I have Chapter 20's top hat problems set up for due on Friday. And I think I sent out the email saying which ones weren't, the problems that weren't, that aren't appropriate. So in terms of naming aromatic compounds, the base ring is a benzene ring, and then depending on what's attached to it, it may or may not change the name. So for instance, if it's just a regular sort of alkyl group, it's the common name of that alkyl group plus benzene. So you can have things like ethylbenzene, isopropylbenzene. But when it's methyl, that changes the name to toluene. And when there's more than one methyl, it changes it to a xylene. So these are common names that have been accepted as IUPAC names. An OH is a phenol. An OCH3 group is called anisole. And then NH2 is an aniline. The xylenes can be either ortho, meta, or para, and I'll go back because we'll actually start using those this week. And then the carbon attached to the benzene ring is a benzyl group, benzyl carbon, and depending on what's attached to that, it would change the name. So you could have a benzyl alcohol, benzoic acid, as well as a benzaldehyde. So those are sort of the common base names, and then from there you might have a group attached, and you would either call it a 1,2 or a 1,3 or an ortho or meta. So if you had a methyl group, for instance, attached here, you might call this either 3-methyl anisole, or you could call it ortho meta. Ortho meta, you could call it meta methyl anisole. Just so you know in terms of the naming. And you can read more about that if you'd like. So we're going to need to remember what ortho, meta, and para are. It's always relative to a substituent. And so if you have only one substituent on there, the ortho position is 1,2 to that, 1,3 meta, 1,4 para. So you're going to want to remember those, because what we're going to find out towards the end of Wednesday and probably into Friday is that when I start to add a group to the ring and there's already a group on there, this group is going to be called the ortho, the meta, or the para director, and it's going to tell that group where to go relative to it. So that's why we have to remember those. So let's talk about reactions of the groups that are attached to the benzene ring, but we're going to start with just a reaction of the benzene ring itself. So the benzene ring itself is aromatic. That means it's super stable. It's going to be very difficult to break up that aromatic ring, but it can be done. And the way that it's done is by pure reduction. So when you take sodium metal and liquid ammonia, the sodium has an electron, one valence electron, And when we dissolve that in liquid ammonia, what we end up doing is forming a sodium cation and then what's called a solvated electron. So that solvated electron, when it's given to a molecule, that molecule gains the electrons. It's a pure reduction. And so this is the kind of purest reduction that you can get in the strongest one. What's going to happen is that benzene ring is going to be broken up into an isolated diene. So there's going to be two double bonds, and the two hydrogens that were added, since it's a reduction, those two hydrogens are going to be opposite 1,4 or para to each other. And there's a reason for that, which I'll show in the mechanism. Okay, so this is called Birch reduction. You're reducing the benzene ring down to a non-aromatic system. So the way the mechanism works is, and these should all be half arrows instead of full arrows. I'm not going to ask you to reproduce this mechanism, but if you want to know why the two hydrogens end up adding para, this is the reason. So what you end up doing is adding an electron to one of the carbons, and then the other electrons move around so that at the end you end up with a pair of electrons on one carbon and an unpaired electron at the end. This would be what we would call a radical anion. And because these are big clouds of negative charge, they're going to have to be as far away from each other as possible. And so that means that they're going to adopt the 1,4 or the para orientation. Now, if you go back and you remember at the beginning of the semester, which was a long, long time ago, we had a triple bond and we reacted it with sodium, metal, and liquid ammonia. And what did we get? A transalkene. The reason for that transalkene was because we basically made a radical anion where we forced the two lobes, which ultimately got the hydrogen, to be trans because they had to be far away from each other. So, same thing here. This is why we end up with a para, with two hydrogens being added para. And we end up with the isolated double bond. Okay. And then we can continue on, and that's how we get that. Again, this mechanism is there just to show you how we get the para product. What if there's an alkyl group already on the ring? If there's an alkyl group already on the ring, you want to place the double bonds so that that alkyl group is attached to it, because what you'd like to do is you'd like to make the most stable of the products. Okay. So the R group is always going to be attached to a double bond. Right, so that's Birch reduction. And the whole idea there is to break up the aromaticity of the ring. Now, when you have a side chain, or when you have an alkyl group attached to the benzene ring, and you're going to do reactions on those side chains, the important or special carbon in this case is going to be the benzylic carbon. And with that carbon, we can make an anion, we can make a radical, and we can also make the carbocation. The carbocation at the benzylic position would be the most stable, as would the anion. And if we free radically halogenate an alkyl benzene, the bromine is going to go to the benzylic position primarily. Okay. So that's the special position. So if we want to take a look, in this X, that X should really be an R, because it's not a halogen, it's just some other group. So we can replace those with Rs. So let's start with the benzylic radical. We know that the benzylic radical is stable because I can write a lot of resonance structures, well, 3 more, into the ring, and so that would stabilize the pi, or the unpaired electron, by resonance structures. Now, if I wanted to, for instance, brominate that position, if I wanted to take a benzene ring, take like propylbenzene, I could use something like bromine and light, and it would brominate at that position. And it would brominate exclusively at that position. Why? Because that's going to form the benzylic radical, which is the most stable. You might say, well, wait, are you sure you can do that with bromine and light? Because you can't do that with bromine and light if there's just a double bond here, not a benzene ring. Right? The bromine always adds to the double bond. But in this case, because benzene doesn't react with bromine, you can go ahead and do this. You could also do this with the NBS reagent as well. So either one of those will brominate at the benzylic position. Okay. So that's the first thing that we have to realize, is that when we free radically halogenate, we're always going to brominate at the benzylic position. Now, carbocations are going to be stable because if I have a benzylic carbocation, I could take this pair of electrons and move it there, and I could now start to write a series of carbocations where the plus charge is in the ring. And so there would be 2 more resonance structures that you could draw that would stabilize that benzylic carbocation. So whenever you have the opportunity to form a benzylic carbocation, that's going to be, and I'm saying this because I'll tell you later, we've found a situation where this isn't the case, which is driving me up the wall. But for the most part, that benzylic carbocation is going to be stable. So I could, for instance, set up a problem where I could do basically kinetic and thermodynamic products like we just did, only now the benzene ring is going to have an effect because it's going to make one of those carbocations more stable than the other. So benzylic carbocation is stable. We have to take that into account. The carbanion at the benzylic position would also be more stable because I could take this pair of electrons and move it here, move this pair of electrons out to that carbon, and I could start writing resonance structures, of which there would be 2 more, where now the negative charge is in the ring. And so then I could take this one and put it here and put that one there. So the benzylic carbon is the most stable, or it's a special position for both radicals, cations, and anions. And we know the only way we really know to make a carbanion would be as if this was an MgBr+. And so if we wanted to make that, we're actually going to be able to, because if I brominate the alkyl benzene, I'm going to brominate specifically at the allylic position, and then when I add magnesium metal to it, that's where the most stable anion is going to end up. So we have to be careful that we take the benzylic position, and anytime there's a charge or a radical there, that's going to be more stable than it would be in nearly any other place. Okay. So that kind of basically opens up a lot of different reactions that we can do with an alkyl benzene, including all the stuff that we've done. All right. And you'll see that in some of the practice problems, as well as I'll put some of those together for quiz problems this week. All right, so everybody kind of with me so far? So we free radically halogenate at that position. We form the carbocation at the benzylic position. The anion would be most stable there. So here's what we did in lab last week. For those of you in lab right now, if not, what we've done is we started with this molecule, and we next reacted that with an anhydride so that we basically converted the amine to the amide. And the reason that we did that was because in the third step we then reacted this with CaMnO4. So what CaMnO4 does is it oxidizes alkyl groups attached to the benzene ring. It does not matter how long that carbon is, chain. Could be 1 carbon, could be 100 carbons, doesn't matter. What happens is it cleaves anything off of it and turns the benzylic carbon into a benzylic carboxylic acid, which is called benzoic acid. So what we did 2 weeks ago in lab was we reacted the methyl group on this molecule with CaMnO4, and it has now become the carboxylic acid. And one of the things we're going to see this week is that an NH2 group can also be oxidized. So the reason that we had to put this, the reason we had to convert this to the amide was I didn't want to oxidize the NH2 group at the same time. And CaMnO4 would have done that. So we just wanted to oxidize the methyl group. So we had our purple potassium permanganate, which took me 2 hours yesterday to clean out of all the balances because I had to take the balances almost apart and throw everything in the sink, at which point it turned purple because there a little speck of that stuff, when you start wiping it down with the paper towel, just turns everything purple. So if there's anything purple on the balances this week, it's because I didn't catch it, but I sure as hell tried. It was everywhere. And then I didn't wear gloves, so I have brown spots on my hand from where it turned from CaMnO4 to MnO2. So just for this, what we're going to do is we're going to take off the C double bond OCH3 group in step 3. And that's going to create a little bit of a problem because then I'm going to be making a carboxylic acid with an amine in it. So the carboxylic acid is going to protonate the amine. So I'm going to end up with a zwitterion that's not going to be soluble in much. Like if I wanted to take an NMR of it, which the NMR is still not fixed, which is also aggravating. I'm going to have to find a good solvent to dissolve it in because it's going to be in an ionic form. And if you go on and take biochemistry, you'll learn about that because in biochemistry you have these things called amino acids, and the amine gets protonated by the carboxylic acid there. So that was where we were at. So we use this reaction very effectively to oxidize the alkyl group to a carboxylic acid. So that's how we can oxidize alkyl benzenes. And you could use potassium chromate, but that's chromium 6, so that not very environmentally friendly. What else about that benzylic position is special? SN2 reactions of benzylic halides generally react faster. Why? Well, in order to answer that question, I need to write the transition state, the SN2 transition state for this reaction. So I'd have an hydroxide substituting for the iodine. I would have, I'm going to write my benzene ring down here. And then up here I would have my 2 hydrogens. So to explain why benzylic halides react faster, it's going to be all about stabilizing the transition state. If I can stabilize that transition state, it's going to be more stable, lower activation energy, faster reaction. So what am I missing in this transition state? Charges. So where should the charges go? Oxygen, delta minus iodine, delta minus carbon. We usually forget about the carbon, right? Well, let's not this time. So that's going to be a delta plus. It started out delta plus because it was attached to the iodine. What? So now that's the critical part. Because what is this benzene ring going to do to stabilize that delta positive charge? It's going to do the same thing that it would with a carbocation. May not delocalize it, but you might as well. But what will happen is, remember, the structure of a benzene ring looks like this. Actually, this is how all aromatics look, right? They've got all sp2 hybridized atoms, all the pi orbitals, or all the p orbitals are parallel, so they make this humongous pi system. And if you think about that carbon, it's going to be able to push a little bit of electron density into that carbon through that pi system. If this was a full-blown carbocation, if that was a full-blown C+, then you'd want the empty p orbital to be, this is empty, you'd want the empty p orbital to be aligned so that all those orbitals could then kind of push a little bit of electron density into that orbital, which I think is a problem. If the carbon can't perfectly align, then you have some difficulties. So that's why a benzylic halide reacts faster, is because the benzene ring helps stabilize that delta positive charge that we don't normally worry about.
Right, I still don't see why the carbon is plus, because in the beginning it's still neutral and then at the end it's neutral. So would it be? Well,
so iodine's more electronegative than carbon, right?
Yeah.
So when we started out, this carbon would be delta positive and that would be delta minus.
That.
Yeah. And that's why the nucleophile will come in and attack that electrophilic carbon. So in SN2, that carbon's always been slightly positive. It's just we haven't written it in the transition state all the time. Some of you have, but we haven't done it consistently. Okay, so the benzene rings help stabilize that, lower the activation energy, and then make the reaction go faster. Okay. So, sort of illustrate some of these issues. How would we prepare? Well, let me start by, this molecule right here is called methylstyrene. Styrene itself is that. It's got the double bond, a double bond attached directly to the benzene ring. So you probably have heard of styrene in terms of styrofoam, which is polystyrene. Polystyrene doesn't have to be styrofoam. Polystyrene is just what happens when you take this chain and make a long chain out of it, a long chain polymer, which sometimes means plastic. If you take that styrene, you can make a polystyrene. What makes styrofoam is that you inject a gas into that so that when the polymer hardens, it has gas cells in it, which makes it float, or which makes it a great insulator for fast food. Right. I'm not sure that the styrofoam is out there too much in fast food anymore. It was there was a chemical company called the Huntsman Chemical Company that basically grew or became the Huntsman Chemical Company because they were able to make styrofoam containers for like McDonald's back in the day. Now they make specialty chemicals. And the guy who founded it was a chemist, but he literally is one of those success stories where he grew up in like a house with dirt floors and eventually became one of the richest guys. And he's passed away, but like the Huntsman Cancer Center in Utah is one of his legacies. So chemists do sometimes become rich and famous, and if they're really good chemists, they do what he did, which was totally get into philanthropy. So anyway, styrofoam, that's what styrofoam is. You can have hard plastic polystyrene. You just don't blow air into it while you're making it. So that's styrene. This is called methylstyrene. So how could we make methylstyrene out of propylbenzene? And we could do it in 2 steps. So what would be the first step to do?
You want to brominate the LO.
So the first step I would want to do is I would want to put a bromine in the benzylic position. And if you go back and think about what could I do with that alkyl group, right? And it's not like you have to remember back, I don't know, days or months. You just have to remember back minutes. The only thing we could really do with that alkyl group is oxidize it or brominate it. And that's true of any alkane. The reason that it's sad we just talked about free radical halogenation with it in the last month is, and not first semester, is because if you have to start with alkanes as your starting material to make all these molecules, there's only 2 things you can do with an alkane. You can burn it, which is fine for driving a car, but not so good when I'm trying to make a bigger molecule out of it, because CO2 and water doesn't help me. Or you free radically halogenate it to put a bromine on that alkyl group, and once you got that bromine, what can you do with it? Turn it into an OH, make a double bond out of it, right? And so now we can do all of our reactions that we've learned so far and more, but we need to free radically halogenate first. So you can think of the alkyl group attached to benzene the same way. First step is I need to put something on it that I can react. Let's put a halogen. Then how would I get from the halogen to the double bond? You've answered once. I learned over break I should be randomly calling on people. Oh, sadly, I left my iPad upstairs. I still can. No, I left my phone upstairs too.
You have your dice?
I have no dice. I have nothing to randomly call on
I
somebody.
don't get to be called on.
What do you think? What? Do an E2 elimination. So what reagent would I use for E2? What? NH2 minus or tertiary butoxide. So I could use NH2 minus or tertiary butoxide. Does it matter in this case? Now remember, with E2, we always have to go back to the basics. Here's my alpha carbon, here's my beta carbon, here's my beta carbon. How many hydrogens on the beta carbon to the left? 0. Right? And that's why I don't write benzene rings with circles in them unless I'm in a rush. Because sometimes when you write the benzene ring with the circle, you forget what it means. So there's no hydrogens there. There's only two hydrogens on the beta carbon to the right, and so that means it doesn't matter what base I use because I can only get one product. And then here we could use either Br2 in light, or we could use NBS. So since we're halfway through the semester here, we should begin to think a little bit more about how to string reactions together. And so usually our first step is going to be to brominate something, or chlorinate it, or brominate it at a high temperature versus low temperature. So then, so in this case I'm using the special position of the benzylic to put the bromine there to then form the double bond. And this double bond is the preferred place for a double bond to go with the benzene ring, because this double bond is in what with the benzene ring? That double bond is in starts with a C. It's in conjugation with the double bond. So it's in conjugation with the double bond, and all of our dienes were special because they were all in conjugation with each other. Right, another thing we can think about is what's the major product of this reaction. I am going to change this to HCl because I know what the answer should be. Actually, I know what the answer is if I go to the lab and do this, because we've done this within the last couple months. So the real question here is, same methylstyrene, actually called beta-methylstyrene. I'm adding HCl, right? Whose rule am I following? Markovnikov's. So where should the H go? On A or B? Or should I get a 50-50 mixture and it goes to both A and B? How many people say A only? The hydrogen is going to A only. B only. 50-50. Don't know. So if I'm looking at Markovnikov's rule here, I have two carbons with the same number of hydrogens. Right? So by Markovnikov's rule alone, I'd expect to get a 50-50 mixture. But if we broaden Markovnikov's rule out, then the H should be added to the carbon that produces the most stable carbocation. And in that case, what would we expect? Well, since I made this big deal about the benzylic carbocation, I probably would say that that hydrogen should add to B so that I form the carbocation at A. And then my chlorine comes in and adds here. So that by our broadened definition should be the major product. And it is. Although it's surprising how slow these reactions are. When you look at them on paper, it seems like they should be really quick, but if we add HCl to this methylstyrene, I think we stirred it for a week and the reaction didn't go 100%. And then we found another way that took 3 hours. And we were only reacting like 2.2 grams. So even 3 hours is a long time. So I'm I'm a little surprised at how long these reactions take, because they seem like they'd be easier than what they are. And that's the product you get. So I come to the conclusion that secondary benzylic versus secondary carbocations, the benzylic tips the scales. And this is 100%. We get 100% of that product. There is no other product. And we can tell that because because when we have a working NMR, we can do this and get the NMR of it. Which right now I just have a half NMR that I bought a $22,000 service contract on. And the first problem was solved with $1 fuse. So, wasn't a good spring break for me. Or for the engineer that had to fly up from Florida while it was super cold and try and fix something that didn't get fixed. He still gets paid. So that's what happens. So what I would normally do in this case is I would just to show you, I would normally say, okay, so here would be a great experiment to do. How about I just put another methyl group on there? And my question is, so what's more stable then? Secondary benzylic carbocation or a tertiary carbocation, right? And so that, in previous semesters, I go, oh, that's a pretty good question. And then I go through and I write the answer, and it's completely wrong. Because when we do this experiment, as far as I can tell, we are the second set of people to do this experiment. The H adds here, and the chlorine adds there. Which when we found this paper, they said, oh, it's the Markovnikov product, which certainly is. The H added to the carbon with the most hydrogens, but they didn't think, this is why I don't like to use the big mode, because it keeps going back and forth. That is the Markovnikov product, but they didn't say, oh, that doesn't quite make sense because benzylic carbocation should be more stable. They just totally bypassed that. So, I guess, tertiary beats benzylic secondary, but I would like to know why. After we got this experiment done, Brian, who was sitting there last year, he goes, I don't think I believe anything you taught us last year. Because this doesn't make any sense. And I said, well, I'm beginning to wonder that myself. So we're going to leave that example off for the time being, because we know what the answer is, but we just don't know why. And now we have to use the computer to try and figure out which carbocation is most stable. And I suspect it has something to do with the fact that the benzene ring can't be perfectly flat and overlap all those orbitals, but that's not necessarily what the computer is telling us. And the computer is just a computer. So we can't make a whole lot of that out of that, except it follows Markovnikov's rule. So in this case, the broadened, well, you know what? We don't know. We don't know what a benzylic carbocation. We don't have all these steps, like what's a tertiary more or less stable of? What's a benzylic more or less stable of? We know benzylic secondary versus secondary benzylic secondary wins. Josh?
For that last example, does it go to 100%?
Yes.
Oh.
Actually, it does more than that. It does more than that, because what we're actually adding is, to this reaction, we're adding DCl. Because we're doing this, but we're determining the products where the deuterium goes. And if you're up on your NMR spectroscopy, the carbon-13 signal is split by protons unless you decouple it, which we talked about in my class. But if the carbon has a deuterium attached to it, it gets split. So I know the carbon that the deuterium is attached to because it's split into a triplet. It's no longer N+1, it's 2N+1. So I know exactly what carbon the deuterium's attached to. And what threw us off was that at the end of this, the deuterium is attached to this carbon, and there's some deuterium over here attached to that carbon. So what that must mean is that when we have the tertiary carbocation, that one of those hydrogens leaves to form a double bond, and then some DCl adds to that. So it's a lot more complicated than it looked to begin with. So then we're stuck. Then the NMR broke, and then we're stuck. Actually, we're not stuck because we already know all this. So it's a little more complicated. So sometimes when I just make up an example, sometimes I'll say that'd be a pretty good experiment to do. I should probably never do those experiments because they always end up exactly opposite of what they should be, which isn't bad. It's not going to gain any notoriety, no fame or fortune, but it's interesting and frustrating at the same time. And then students question what you're teaching them, which is the case. Although when I give a talk about it, I probably could put that up and ask the entire room and probably get some arguments, if not fistfights, over the answer. Just asking people, like, which one should it be? But until I know what's going on, I'm not going to present that. So that's side chain reactions. Okay. So I'll have some problems for you on Wednesday, as well as I have a lot of practice problems on those. So now let's talk about adding things into the ring. Because in theory, that shouldn't happen. The benzene ring is so stable that nothing will add to it. No, not true. We know this. What we know is if you try and take benzene itself and react just bromine with it, no reaction. KMNO4, no reaction. Sulfuric acid and water, no reaction. So all of these would be no reactions. So I'm going to need to do something a little bit more to get an electrophile to add into the ring. And I know I need an electrophile because this benzene ring has nothing but double bonds, so it's nucleophilic. So I'm going to need something with a positive charge to add. And so that's what I'm going to do, except that normally when we add an electrophile to a double bond, we add the electrophile to one carbon and the nucleophile to the other carbon. That's not going to happen. What I'm going to end up doing is substituting an electrophile for a hydrogen on the benzene ring. And that's going to be called electrophilic aromatic substitution, as opposed to electrophilic addition, which is what we have been doing. Okay, so that's what we need to do. And so in order to do that, let's talk about the mechanism. So if I add an electrophile to the double bond, if I can make an electrophile strong enough to add to the double bond, it will. And so then I'll end up with this allylic carbocation. And what will happen to that allylic carbocation? It's going to form resonance structures. So a pair of electrons is going to move there. And then the plus charge would move over one. But I don't have to write that because I already wrote it out. And this is kind of dangerous because, you know, then everybody's sitting there sleeping. But don't worry, I'll make you do this at some point yourself. But basically that plus charge can go over one and then it can go over one again. So there's 3 resonance structures that you can get for this carbocation. And you can write the resonance hybrid for that, for those 3. Did you
So you don't that it's not a that's not a 100% product then. It's only a major product, because then you have the other resonance structures, right? Or does it?
Oh, well, so here's the thing. If this was a non-benzene ring, we would expect to get 1, 2, 1, 4, and 1, 6 products by this mechanism. Well, let's go to the next slide and see why that won't happen. Okay, so if this was what we had done previously, the nucleophile could add to any one of those carbocations and we would get 3 different products. And what I've done is just shown, okay, maybe the nucleophile adds up here. But if I add the nucleophile to any one of those carbocations, what did I do to the benzene ring? I destroyed it. So this system, this product isn't aromatic anymore, which means that it's not super stable. So what this system decides to do is it wants its super stability back. Again, I'm giving these things human characteristics like they have a choice. But to be honest with you, they don't have a choice, because everything's driven by energy, either enthalpy or entropy. That's the world of chemistry. You don't get a choice. It's whatever that tells you it will be. So instead of the nucleophile adding to the carbocation, I lose the H plus and move that pair of electrons back in, and we reform the double bond. And that reforms the aromatic ring, makes the product super stable, and so we don't end up with electrophilic addition, we end up with substitution. So we don't have to worry about doing 1, 2, 1, 4, and 1, 6. All we do is we just write the resonance hybrid or write the resonance structure, but then we're going to lose an H plus, and we're going to substitute the electrophile for that H plus, for that hydrogen. So we're going to do electrophilic aromatic substitution. It's all because we need to form that stable ring again.
Do we have to add another nucleophile in for that to happen?
No, because here's the resonance structure that I had formed. Here's my. So what's going to happen is this hydrogen is going to lose its pair of electrons, and so I'm going to end up reforming the double bond there, and now the electrophile has substituted for that hydrogen. Right? So that's what's going to be different about these reactions with the benzene ring. I'm going to do substitution, not addition. So now all we need to do is learn all the reagents to make all the different E pluses that we can add to the ring. So we start off with the big 3 here. You want to add a nitro group to the ring, HNO3 and sulfuric acid. What ends up happening is the sulfuric acid protonates the nitric acid, it loses water to form NO2+. Sulfonation, take SO3, sulfur trioxide, add sulfuric acid to it, and you protonate the SO3 to make SO3H. Why do you make SO3H? Why is that important? Because that lets me make a sulfonic acid. A sulfonic acid is a pretty strong acid because its conjugate base has lots of resonance structures. That OH group is just one atom away from being a sulfonyl chloride or a tosyl chloride. And so that sulfonic acid can That OH can be converted to a Cl, and there's my tosylate to make tosylate esters out of. And then finally, you can halogenate, but you need more than Br2. You need Br2 in either FeBr3 or AlBr3. And so what happens there is the iron rips one of the bromines off of the Br2, and you end up with basically the Br plus or Cl plus. So these are the first three reactions we can do to make an E plus. Once I make the E plus, I'm going to add to the ring, and I'm going to make my product. On Wednesday, we'll start with pretty boring stuff. I'm going to add them to a benzene ring. Well, benzene has 6 hydrogens that I can add to. That's boring. Let's put a group on there and then add these electrophiles. So if I have a group already on the ring and I add the electrophile to it, where does it go? Ortho, meta, or para? And why? Right? And then, once we know all those reactions, then I can give you a benzene ring and a molecule and say, make it. And how many ever steps you need. And that'll be Friday. So that's where we're going. So we're just starting with, let's make some E pluses and add them to the ring. Okay. All right. So I have aromatic, non-aromatic, anti-aromatic problems for you up here, and then I'll hand back your